In this video, I'll provide an introduction to structural equation modeling. I'll explain what it is and what it is used for. So structural equation modeling is a linear model that um, can be thought as a very general model that has regression, path analysis, and confirmatory effect analysis as special cases. Um, so regression is a method that where you have just one outcome and multiple predictors, and they only observe variables, such as, for example, the individual's wages or hours of work. Um, Path analysis is a generalization of regression analysis, where you can have multiple outcomes analyzed simultaneously and multiple predictors. So, for example, if you're interested in both, let's say, work hours and wages as outcomes, if you were doing regression analysis, you'd have to run two regression models. But in path analysis, you can run with those two outcomes simultaneously. And it allows you to as examine mediation moderation in a more straightforward way than regression analysis. Now, confirmatory factor analysis is about measuring latent variables. So a latent variable, for example, is intelligence. You cannot see intelligence directly, only manifestations of intelligence. So you need an intelligence scale to measure intelligence, but every scale measures a latent variable with error. So confirmatory effect analysis is a statistical model that tries to take responses to a scale that is intended to measure a latent variable, separate measurement error from the actual latent scoring on the latent variable. Now, structural equation modeling combines confirmatory effect analysis and path analysis. You can have multiple latent variables as either outcomes or predictors, and you can have observed variables as well. So this is an example of path analysis. In structural equation modeling language, we call variables that are being predicted. In this case, which in regression we call outcomes. In path analysis, in structural equation modeling, we call these endogenous variables. So need for achievement here and GPA are endogenous variables because they have arrows arriving at them. They're being predicted. And variables that are predicted, so they don't have any direct effects arriving at them, there is only a correlation between them here. Those are exogenous variables. So this model has two exogenous variables, IQ and SS. Direct effects are these arrows that hypothesize causal relationships with a certain direction. So, for example, B here is a direct effect from SES to need for achievement. Indirect effect is when there is a mediator. So, for example, between SES and GPA, there is a mediator which is need for achievement. And spurious correlation is where there is no causal hypothesis. So the relationship between IQ and SS is spurious because it's just a correlation. So this is an example of confirmatory effect analysis. So we have here a set of items that measure criticism, a set of items that measure positivity, and a set of items that measures the over-involvement. And so these items are being separated in two parts: measurement error, which is here on the right, and these arrows here are the relationships between the latent variable and the item. So 0.37, this is known as a factor loading. 0.37 is the relationship between criticism and the item that measures criticism. So structural equation modeling combines path analysis and confirmatory effect analysis. So for example, this is a very complex structural equation model. We have here for the ellipses are latent variables, the rectangles are observed variables. So we have here job satisfaction, Um, is a latent variable measured by three indicators, which are items, faces, duty, and theme. Um, Inter-row conflict is measured by family, personal, and community. Um, and each of these rectangles have a measurement error associated with it, but it's not showing the picture. And then the direct relationships between the latent variables are these darker arrows here. You can also have a structural equation modeling where each latent variable is measured by a single indicator. This is an example. It's not ideal that latent variables are measured by single indicators because then you can't separate the measurement error. It's better if you have at least three measures of each latent variable. So structural equation modeling is a process that has multiple steps. First, you specify a model according to theory. Then you evaluate identification, which is to evaluate if you have the right amount of data to estimate that model. Then you select measures. That is usually done with to get 1, 2, and 3 are done typically together. Then you prepare your data, deal with outliers and missing data in that step. Then estimate the model and evaluate model fit, which means does the model represent the data reasonably well. If model fit is adequate, you interpret the results. If model fit is not adequate, you have to re-specify the model using alternative theories and other sources of information. They consider the alternative models and report the results. So what type of research designs can use structural equation modeling? Well, any type of research design. Structural equation modeling is a very flexible method. So the most common is correlational design, where you just are estimating relationships. You measure variables, and these variables are obtained from surveys, archival data, administrative data, computer logs. You can combine all these sources of data, and there is no random assignment or conditions. So there is no treatment and control group. In an experimental design, the objective is to estimate the treatment effect, and there is random assignment to treatment groups. The most common is to have a single treatment and a single control group, but you can have experimental designs with multiple treatment groups. You can even have experimental designs where individuals are assigned to dosages of treatment. The key for an experimental design is that individuals are randomly assigned to conditions. Now, quasi-experimental design has the same objective as the experimental designs. It is to estimate the treatment effect, but there is no random assignment to conditions. So here, methods to remove selection bias are used to compensate for the lack of random assignment. Now, the amount that these methods to remove selection bias are successful depends on the method. You'll never get as strict control for selection bias as you get with an experimental design when you're using a quasi-experimental design. So correlation designs, a very common misconception is that it's the same as survey research. You can collect data for a correlation design with survey, but for example, you can use data from archival data from databases. You can use computer logs from online management system. Any type of data that's secondary can be used in a correlation design. So correlation support causality, but the quality of evidence is much weaker than in experimental and quasi-experimental design. So causality is a matter of argument, and you can have a very strong argument for causality with an experimental design, or a lot weaker with a correlational design, or somewhat in the middle with a quasi-experimental design. One important thing to understand is the different types of relationships you can have in structural equation modeling. You can have a direct relationship, such as alcohol consumption leads to loss of motor skills. You can have an indirect relationship where there is a mediator. So alcohol consumption leads to loss of motor skills, which leads to car accidents. In fact, there can be an infinite number of mediators in between two variables, but that are causally related. But sometimes you don't have measures of those mediators. Um, and then spurious relationship is a relationship that's not causal. A classic example is in a hot day, the relationship between incidents of drowning and consumption of ice cream. They are both related to temperature. With hotter days, people swim more, so more vulnerable to accidents of drowning, but they also eat more ice cream. There is no causal relationship there, it's just a spurious relationship because there is a confounder variable, which is temperature. So this is an illustration of how correlation really doesn't say anything about causation. So here on the right, we have a structural model showing the causal relationship. Um, Notice that V3 has a direct effect of V2, and it's plus 0.8. V1 has no effect on V2, the coefficient is 0. However, there is the correlation here between V1 and V2 is 0.56, so there is a positive correlation even though there is no direct effect. How does that happen? It's because the correlation is the sum of the 0 here, but also the product 0.7 and 0.8, because you can get from V1 to V2 through V3, so you can go back on this curved arrow here, which is a correlation, and then this way. And that's why you get a correlation that's 0.56, and that correlation is really just due to the correlation between V1 and V3, that's 0.7, and the direct effect of V3 and V2, which is 0.8. Also, this is an example where the correlation is 0, but there is a direct effect, so there is a suppression effect here. So the direct effect of V1 over V2 is plus 0.36. However, V1 is related to V3 at plus 0.6, and V3 has a direct effect of V2 that's minus 0.6. So the total correlation is 0.36 plus the product of plus 0.6 and minus 0.6, which is 0. And that's how you end up with a correlation of 0. Now, this is an example where the correlation is negative, but the direct effect is positive. So it's also another suppression example. Here, what happens is that the direct effect is 0.2. However, the spurious relationship is the product of minus 0.6 and 0.7, which is minus 0.42. Therefore, the correlation is minus 0.42 plus 0.2, which is minus 0.22, which is the correlation observed here. Now, here is an example of SEM for correlation research. So in this model here, to estimate this model, Carmelli, Bejardo, Waldman, and Rook, they sampled employees and measured with a survey leader relational behavior, body social capital, vigor, and job performance, and then fit the model to the survey data where leader relational behavior predicts body social capital, which predicts vigor, which predicts job performance. Now, this model, the representation here is simplified because every ellipse here is a latent variable, so there are indicators here for each of them that were omitted from this feature. This is an example of SEM for quasi-experimental research. So in Leite, Stapleton, and Bettini, the objective was to estimate the treatment effect of teacher participation in a network, which is shown here. This is a latent variable model. These are latent variables here, perception of school management and others that predict workload manageability. The endogenous variable of interest is workload manageability. And so the main interest is estimating the treatment effect of participation in the network on the manageability. but it wasn't experimental design because teachers were not randomly assigned to be in the network. But in this article, propensity scores were used to remove selection bias. Then you have an example of SEM for experimental research. So in Mays and Potsakoff, 2014, students were randomly assigned to conditions in experimental design. So there was a manipulation here, and the effect of that manipulation and the grouping of students into treatment and control. The effect of that manipulation was estimated. The effect of this latent variables, supportive voice, constructive voice, defensive voice, destructive voice, and loyalty. So this is an example for SEM for experimental design. The advantage of SEM for experimental design is that you are able to estimate effects of treatments on latent variables. So that's the introduction to structural equation model.